millimeter cube, and this is equal to 77.5 times 10 to the power minus 6 meter cube now. Okay. Then if we calculate the Q over T ratio, and the Q over T ratio at point B now, so this will be equal to 77.5 times 10 to the power minus 6. The thickness now is 0.02, and this is 1 because we only have Q. Okay, so 77.5 power of 6 minus 6 divided by 0.02 divided by 1 is 3.875 times 10 to the power 3. Okay, so that is our minus 3, sorry. Okay. So at point C is 2.25. Now we increase to 3.875 at point B. Okay. Then finally at point A, we now have to look at non-thin wall analysis. So for non-thin wall, the thickness is equal to what? The thickness is equal to 0.12 meter. Okay, so that's for non. So now we have to consider all this area that I'm highlighting in yellow. We have to consider this area over here, and this entire area over here. Yeah, this entire area. So from here, so the Q at point C. Oh, sorry, point A. Come on, Eugene. So the Q at point A will be twice the Q of point B, right? Because if you look at point B, you have left and right now, right? You have the left section and the right section. Then plus by the width. So the width is 120. The depth is 30. The y bar is 30 divided by 2. Okay. So this is good. Twice the Q at point B is 77.5. Plus by 120 times 30 divided by 2, 54. So this is equal to 2.2 times 10.5 power 3 plus by 54 power 3 is equal to 209 times 10 to the power 3. Or 209 times 10 to the power minus 6 meter cube. Okay, so now if we look into the Q over T ratio at point A now, so this will be equal to 209 times 10 to the power minus 6. Now the thickness is at 0.12. Okay, so no doubt the first moment of area is the biggest. Likewise, it also has the what? The biggest or the highest thickness. So this is equal to 1.742 times 10 to the power minus 3. Okay. So from here, I'm just going to write on this side of the paper, so I don't need to flip around. Okay. So to compile our data now, we know that Q at point C is 2.25. Q over T at point B is 3.875. And Q over T at point A is 1.74. So we know from here, right? At point B, Q over T ratio is at its maximum. right? So therefore, we know that the highest, so it's 75. So therefore, tau max is equal to shear at point B, and this is equal to V over I multiplied by 3.875 times 10 to the power minus 3, right? So from here, the tau max is equal to 75 times 10 to the power 6, and our V over I ratio, this is equal to 3.875 times 10 to the power minus 3. So our V over I ratio will be equal to 75 power 6 divided by 3.875 power minus 3 is equal to 19.355 times 10 to the power 9. Okay, and this is in Newton per meter 4. Let me do it again. 75 power 6 divided by 3. Yep, 19.355. So from here, we can calculate the shear stress point A, which is equal to 19.355 times 10 to the power 9 multiplied by, at point A is what? Sorry, not at point, yeah, at point A is 1.742. So 19.355 power 9 times 1.742 power minus 3 is equal to 33.71 716 megapascal. Let me do it again. 19.355 power 9 742 power minus 3 is equal to 33.716. And the shear stress at point C again is 19.355 times 10 to the power 9 multiplied by 2.25. Is it 2.25? Let me see. Yeah, 2.25. So 19.355 power 9 times by 2.25 power minus 3 is equal to 43.549 megapascal, right? So you can see, right, the shear stress at point, so this is our point C, is higher than at where? Is higher than at point A. Okay, so it's known that for thin wall analysis, the shearing stress will be higher. Okay, so now before I finish off, right? If now I'm just going to show very briefly. Okay, if now what will happen now? Again, if we now for this problem now, I can now change the direction to become what? VZ. Because the left hand side and the right hand side, right, are the what? The geometry is the same. So the stiffness is the same. So from here, we can again, right? We can again, I'm going to draw the geometric datum. Okay, so this is our geometric centroid. So when we design the shear flow, right? So the shear flow will look like this again. And then it will flow this way. And then it will flow this way. And we again found that we have 4 terminals. Okay, so I'm going to quickly do this. Okay, usually quickly result in mistakes, but I'm going to try. So if we look at the first moment of area of point C, right? So now this is our width, right? This is now our depth, right? So we are going to do the first moment of area of about the y-axis at point C. So now the width is equal to 10. The depth is equal to 30, right? So if this is 50, so down here to here, this is 10, right? So this is also 10, okay? So the y bar or the z bar is 10 plus by 30 divided by 2, okay? So for this case, so 10 plus by 30 divided by 2 times by 10 times by the depth, so it's equal to 754, 7.5 times 10 to the power 3 millimeter cube. Let me do the 10, 30 divided by 2 plus 10 times 30 times 10. Yep. Okay. So this is equal to 7.5 times 10 to the power minus 6 meter cube. So if we look at the keyword T ratio at point C, is equal to 7.5 times 10 to the power minus 6 divided by our thickness of 0.01. Okay, so 7.5 power minus 6 divided by 0.01 is equal to 750 times 10 to the power minus 6. Let me do it again. 7.5 power minus 6 divided by 0.01. 750 times 10 to the power minus 6. Okay, that's our Q over T ratio. So now if we were to consider point B, we will have the 7.5 times 10 to the power minus 6 plus. So now the width is 50. The depth now is 20. The y bar is 120 divided by 2 minus by 20 divided by 2. Okay, so 20 divided by 2, 120 divided by 2, the width is 50. Yep. So 120 divided by 2 minus 20 divided by 2 times 20 times 50 is equal to 50 times 10 to the power 3 plus by, I should use millimeter. Okay, so 7.5 times 10 to the power 3. Okay, so let me do it again. 50 Yep. So 50 power 3 is equal to 57.5 times 10 to the power 3 millimeter cube. Okay. Yep. So this will be equal to 57.5 times 10 to the power minus 6 meter cube. So the Q over T ratio now at point B will be equal to 57.5 times 10 to the power minus 6 divided by a thickness of 0.02 now. Right? So 57.5 power minus 6 divided by 0.02. Now the value has increased to 2.875 times 10 to the power minus 3 is bigger now. Okay, compared to what we have. What we have before is 750 times 10 to the power minus 6. Okay. So, or if I were to write this 750 power minus 6, so let's do it in terms of minus 3. Now this is 0.75 times 10 to the power minus 3. Okay, so 57.5 power minus 6 divided by 0.02, 2.87. So now we consider point A, right? So it's twice of the 57.5 because now it's a non-thin wall again. Okay, and then plus the width is 60 right? So now we consider this section that I'm shading now. Okay, so the width is 60. The depth is also 60, right? Half of 120, 60. And this the y by 60 divided by 2. Okay, so this is equal to 60 times 60 times 60 divided by 2 is equal to 108. And 57.553 times 2 is 115. So this is equal to 115 plus 108 is equal to 223 times 10 to the power 3 millimeter cube is also equal to 223 times 10 to the power minus 6 meter cube. So therefore the Q over T at point A now is 223 times 10 to the power minus 6. Now the width is 0.06. Okay, 0.06. So when that's the case, 2 to 3 power minus 6 divided by 0.06. Now it's 3.716 times 10 to the power minus 3. So what you realize that tau max now for this case will occur at point A. Okay, so we have to be careful, okay? Not always if the load shifted, the answer will be the same, okay? That's all I have now. Next week, there's no lecture, so take it as a like reading week break, and I'll see you in the following week. So those of you that have correction to do, the correction is on Tuesday. I think it's June 26th, and I already put the location, okay? Thank you. Bye.
Thank you.
Bye.